Bill is going to give a talk today.
Thank you. So the title of my talk will be tangent spaces and T-invariant curves of Schubert varieties. And this talk it's on some work with Victor Kreiman. And so the general setup is going to be, so I'll try and avoid writing the whole thing down. So X is going to be G mod B. So probably everybody knows what G and B are here, so I probably don't really need to define that. And then the Schubert varieties I'm going to talk about will be XW, and this is going to be the B minus dot WB orbit. So in this notation, the codimension of XW is the length of W. And so we want to consider to look at XW near XB. So I should say, here here, maybe I should just back up for a second. So the T fixed points, so T is a maximal torus, G is B contained in T, and T is a maximal torus, W is the Weil group, and the T fixed points of X are, I'll say even XW, are the points, the XB, where X is an element of the Weil group, such that X is bigger than or equal to W in the Bruhat order. Yeah, yes, I should have put the closure here. Thank you. So when we want to look at this here, and it turns out it's easiest to look at this. We can factor out an affine space by intersecting with a cell. So if I look at this, if I look at B dot XB, this is it's a cell in X, and it's just isomorphic to a vector space. Maybe I'll say even a T representation V. And the weights of V are, so the notation for weights is just phi of V. That's the notation by which we name the weights of V. And these are the set of, it's just the inversion set of X inverse, which is the set of roots, positive roots alpha, such that X inverse of alpha is a negative root. Okay, so V is a sort of a known vector space, and what we look at is the Kazhdan-Lustig variety is YWX equals XW intersect B dot XB. So near the point the point xb, xw looks like ywx cross another T representation. So from the geometric point of view, it's really enough to, well, the geometry that we're interested in is contained in yxw. So it's enough to study. And so the things we want to look at are the following. So yxw can be thought of as a subset of V, which is just a vector space. So the tangent space at xb, the Zariski tangent space of y, wx, is also contained in V. And so this is the space that we're actually trying to understand. So our ultimate goal, which is not achieved, but is to understand this space in this. So because this is a T representation, it's really enough to understand the set of weights of this T representation which is a subset of the set of weights of V, which is just a subset of this inversion set of X inverse. Okay, and so we're going to, I don't want to write this down all the time. I'm going to give this a certain name here. I'm going to call this phi tangent. Because that's a set of, so to remind us that this is the set of the weights of the tangent space. Now there's another space that's easier to understand. So any T-fixed curve in ywx passing through X gives a one-dimensional tangent space. It's a smooth, it turns out it has to be a smooth curve. It gives a one-dimensional subspace of V, which is namely its tangents. The tangent space of that curve is a one-dimensional subspace of V. So let TE X of B, if you like, of Y, WX be the span of all these spaces in V. So then we have TEXB, TEXB of Y, WX is contained in TXB of Y, WX, which is contained in V. So this is what this, so that if we look in terms of the sets of weights, the set of weights, so the corresponding sets of weights well, we have this one here, we called phi tan. That's a set of weights of this vector space. And these weights here are I of X inverse. And then this, let's just give this a name. The set of weights here, I'm going to call this phi cur. Okay, and that's to be thought of as the set of weights of curves. Okay, so this cur is to remind us that this is the set of curves. Okay, and now the interesting thing is that phi cur admits a very simple type-independent description. And that's due to Carrell and Peterson. In type A, the sets phi cur and phi tangent can coincide. But in general,
can you explain what you mean by description of that?
I'll tell you in a minute what it is. If that's it, you can describe it in terms of the Weil group in the Bruchau order.
So is it like a capital form?
Well, no, okay. In fact, so I'll actually tell you what this is. In fact, so phi cur, it's the set of all gamma in I of x inverse, such that S gamma of x is bigger than or equal to W. So it's, in the sense, it's something that you can calculate just basically knowing the Weil group in the Bruchau order. In fact, the condition that the gamma is in I of x inverse forces, it means basically equivalent to is equivalent to x, S gamma of x less than x. So we have this situation here where, for x to be a t-fixed point, I should have backed up here. So here, the assumption has to be that x is bigger than or equal to w here, because that's sort of, otherwise it's not a t-fixed point to begin with. I should have said that. So then what's happening here is that if S gamma of x was bigger than x, it would automatically be, it's sort of uninteresting because it doesn't even see w at all. So that's why we're discarding those things. The things that don't see w at all are the weights where S gamma of x is bigger than x. And in fact, this is basically what Brian Bowe and I were doing something like this a long time ago when we were working on these things. We didn't really, think of it exactly like this, but somehow we found that the combinatorics became simpler when you just discarded these other weights, which really didn't have anything to do with w anyway. They don't have anything to do with, they're only related to the point x itself, and they're not related to w, so directly so. But in other types, phi tan is much more complicated. So in classical types, it was described by Lakshmabai did it. I think in type A, this is basically, I think, Lakshmabai and Seshadri, basically. It's done in Lakshmabai, and you can read about this in the book by Lakshmabai. But in the exceptional types, to my knowledge, it's not known in general, explicitly. I mean, there's some conditions based on representations, but I don't believe it's been worked out, to my knowledge. So, and even these descriptions by Lakshmabai, if you ever look at that theorem in the book by Billy and Lakshmabai, it's a very daunting theorem, and it's like, to even calculate a simple example by hand is the only cases where it's really sort of manageable is if x is the longest element of the Weil group, then these conditions are somewhat manageable looking. Otherwise, I mean, of course it's something that you could do, but you'd have to spend a while just trying to understand what their theorem even said. It's kind of, I mean, of course it's a doable thing, but it's not, you can't just look at it and have any idea what is really going on. At least I cannot. So partly because of this, we'd like to just understand phi tan a bit better. And so the main theorem that I want to talk about today is that if we look at the cone, I'll say over Q of phi tan, this is equal to the cone over Q of phi cur. And by the cone, I mean the set of non-negative linear combinations. And in simply laced types, this would also be true with Z replacing Q. But let's just leave it at that for now. So maybe I'll just do one kind of a small example here to sort of just illustrate this. So for example, let's look at B2 and C2. So in B2, there are 4, and C2, there are 4 positive roots. The positive roots are alpha is epsilon 1 minus epsilon 2, beta equals epsilon 2, S alpha of beta equals epsilon 1, which is alpha plus beta, and S beta of alpha equals epsilon plus epsilon 2, which is alpha plus 2 beta. And in type C2, there's the roots are, again, is alpha is epsilon 1 minus epsilon 2, beta equals 2 epsilon 2, S alpha of beta equals 2 epsilon 1 equals 2 alpha plus beta, and S beta of alpha equals epsilon 1 plus epsilon 2, which is alpha plus 2 beta. So, oops, did I make it that right? That's not quite right, is it? That's alpha plus beta, sorry. It's an alpha plus beta here. Okay. So let's look at, so I'm going to look at XSB beta at X equals W naught. So W is equal to S beta. So in this case, the Kaj-Don-Lustig variety, I mean, basically X is the longest element of the Weil group. So X inverse, the inversion set of X inverse is all the positive roots. So I'm not really taking a slice at all. I mean, because I'm looking at the longest element of the Weil group.
Right. No, just to you scroll one a little bit before this goes away.
Yes.
So you're saying that in all other types in type A, you have a proper inclusion?
In all, I mean, for certain elements of for certain points in Schubert varieties, they can be equal,
Yes.
but they're not generally equal for any other type.
Oh, okay. So
But
are there counterexamples for all those other types?
Well, I think if you, I mean, I haven't explicitly checked, but I mean, I think one could, like, I basically did a few examples in type B2, C2, D4, D4, D5. So I mean, I think I haven't explicitly written down a counterexample in any given type, but I think it would be pretty easy to write down some examples in any type where you'd have a counterexample. I don't have one at hand, but I think it's, but if the point is a smooth point of the Schubert variety, then these two sets coincide. So there are many smooth points of Schubert varieties, and so the sets phi cur and phi tangent will coincide for some points of Schubert varieties in any type. But in general, I think in every type, I mean, I don't know that I've actually looked at G2. I mean, one could calculate G2, I think, for example, but probably. But anyway, if we just look at this type here, it turns out that in B2, XS beta is actually smooth at W naught. And in this case, one can calculate that phi tan equals phi cur And this is just, it's alpha, beta, alpha plus beta. But in C2, it's not smooth. It's rationally smooth, but not smooth. So rational smoothness is the same across types, but smoothness is not the same across types. So this is not smooth. And one can check that phi cur is alpha beta, alpha plus 2 beta, and phi tan equals, it's all 4 roots. But you can see the missing root, in this case, it's kind of easy. The missing root is in the cone of the others. So that's sort of trivial in this case. But you can see that it's just an example where you can see concretely that these two things are different, but one is the cone of the other. And then I worked with the computer, one can do some examples. For x equals w naught, it's not too hard to implement like a computer code to calculate these in like type D. One can calculate these spaces, and one can see what's missing. And in D4 and D5, you can see that you can check this sort of by hand. But anyway, so that's just kind of to illustrate that these two sets are different. And the interesting thing is that this description cannot. Because of this, the Weil groups in Bn and Cn are the same, but it's not really possible, it seems, to sort of come up with a description depending just in terms of the Weil group of smoothness. Actually, you need a bit more information. Whereas rational smoothness, you can get totally in terms of the Weil group. Okay. So the remainder of this talk, I want to just explain some of the ideas that go into why this theorem is true. So the rest of the talk is going to be some explanations. Discuss the proof. Okay, so again, what we have to do is we have to take take a reduced expression for our element x. So write x equals S1, S2 to Sn, the reduced expression. Si equals S of alpha I, a reduced expression. And then, so it turns out that if we define gamma I, you can write the inversion set of x inverse. You can list the elements of this out. There's gamma 1, gamma 2, gamma 3, and so on up to gamma n. And the way you can write this out is you just take gamma I to be S1, S2 up to Si minus 1 applied to alpha I. And so you can explicitly write down the elements of this inversion set. So what I want to think of now is I want to think of there as being two functions so to simplify my notation, I'm just going to call this S for the moment. I know S is often used for simple reflections, but S is going to be this inversion set of I inverse for X inverse for the rest of this talk. So I want to consider two functions from S to the Weil group. So the first function is just X, and I'm going to write what it does to gamma I. And what this is just, it's S1. I omit the root Si from my set and I multiply them together. I can also write this as, this actually turns out to just be S of gamma I of X. So this is actually independent of the reduced expression because it's S of gamma I of X. But the second function I have to consider is a little bit more complicated to define. So I want to define an algebra, which is called the zero Heca algebra. So the zero Heca algebra is the algebra over some field, whatever field I want. Usually I want it over like the representation ring or something, but over whatever, it doesn't, that doesn't really matter in this case. With basis h, basis of h of u for u is an element of the Weil group. So it's got a basis like this. And then the way things multiply together, if I take a simple, so h1 is the identity. And the way things multiply is if I take the element corresponding to a simple reflection, and I multiply by hu, it's h of su if the length of su is bigger than the length of u. And it's just h of u if the length of su is less than the length of u. So the interesting thing about this, for example, is that if I take something like, h of s1, h of s2, h of s1, h of s1, for example, this is the same as just h of s1, h of s2, h of s1, because these two things together just multiply as s1, as h of s1, because the way the length is. So what happens basically is that instead of going back, if I multiplied the elements in the Weil group, what I actually get is just s1, s2. So it's a small. So somehow the zero Heca algebra is giving me some kind of longer elements, and this is actually just h of s1, s2, s1. So in general, if I have a reduced expression, so if I have a reduced expression, say h of s of I1, h of s of I2, h of s of Ik, this is just equal to h of s of I1 to s of Ik. So it just multiplies very simply in the case of a reduced expression. But in general, h of s of I1 times h of s of Ik, it's h of some element, I'll just call it, say, z, where z is some unknown element of the Weil group, where z is actually bigger than or equal to si1, sik in the Weil group. So the de Mazur product of h of s of the sequence s of I1, s of I2 up to s of Ik is just this element z. And so I think that term was introduced by Knudsen and Miller. But so you're basically taking some longer element than you would get by multiplying all the elements together. And so my function z of gamma I, it's the de Mazur product of s1, si hat, s of n. So again, the x's here are the usual product, basically, of the reflections. And these z's are the de Mazur product. And then just for simplicity, we write, xi equals x of gamma I, and zi equals z of gamma I. Okay. So the Carrell-Peterson, the Carrell-Peterson description of phi Kerr can be rewritten as follows. phi cur, it's a set of all gamma I such that xi, which is just x of gamma I, is bigger than or equal to w. Because xi is this s of gamma I times x, what I said before. So that's what that is here. So in terms of this, it's kind of simple. So the key sort of insight to what we're doing here is the following important fact, which is that phi tan is, so by the way, just for notation here, this set here, we can call this set S of x less than or equal to w. Because if we like, we can write this as just the set of all gamma in S such that x of gamma is bigger than or equal to w, right? That's a way of just notating. It's the set of all gammas, whose, when we apply that function S, we get this property here. So in other words, phi of cur is equal to S of x bigger than or equal to w in this notation. So now the key fact that we want to use here is that phi tan is contained in the cone over z of S of z bigger than or equal to w. So now let's pause for a second here and let's look at this. So first of all, so in other words, this is just, so S of z bigger than or equal to w, it's a set of all gamma I such that zi, which is just z of gamma I, is bigger than or equal to w. So zi, remember I said before, zi is bigger than or equal to xi, because in the zero Heca algebra, the length never goes down. So when you're multiplying things in the zero Heca algebra, you get something bigger. So zi is bigger than xi, which implies that S of z bigger than or equal to w is a bigger set than S of x bigger than or equal to w. So this is the first key fact here. But despite the fact that these two sets are different, sort of the key fact too is that the cone over Q of S of z bigger than or equal to w is equal to the cone over Q of S of x bigger than or equal to w. So although these two sets are different, and they really are different, their cones are the same over Q. And so then once we know this, we could prove the main theorem assuming these facts. So the proof of the main theorem of the equality cone Q of phi tan equals cone Q of phi cur. Let me just say how that follows from all this. Well, since the tangents weights are bigger than the curve weights, we have, if we look at this equation here, this inclusion is clear. The cone of the tangent weights is bigger than the cone of the curve weights because there are more tangent weights. But for the reverse inclusion, it suffices to show that phi tan is contained in the cone over Q of phi cur, right? Because then that would prove the reverse inclusion. Once this subset is contained, then its cone is contained in the subset. But so we have phi tan is contained in the cone over Z of S of bigger than or equal to W. And that's contained in the cone over Q of S of Z bigger than or equal to W. And that's equal to the cone over Q of S of X bigger than or equal to W. Okay, so that's the proof of that equality there. But it's not actually true. It's not true that phi tan is actually equal to S of Z bigger than or equal to W, though. So that's sort of what one might like for the, one might hope that you get a description that's just like the Carrell-Peterson description, but that's actually not true in this case, because even in type A2, one can find an example where it's not quite right there. So in fact, I would say, this is still, it's a little bit mysterious in the sense we don't completely understand everything here, but okay. So in the remainder of the talk, maybe I should explain a little bit about why fact 1 and why fact 2 are true. So maybe I'll so maybe in the interest of time, maybe I'll say a little bit about fact 2, because at one point, in my last talk, I said some stuff that was closer to fact 1. So I didn't exactly say fact 1, but I said stuff that was closer to it. So maybe I'll just sort of explain a little bit why fact 2 might be true. So from the previous kind of, if one is looking at cones, one wants to look at kind of the indecomposable elements of the cone, because you'd like to, if you're doing with roots, the positive roots are all contained in the cone in a cone, and the sort of the vertices of that cone are where the simple roots lie. So if one is considering cones, one always wants to consider indecomposable elements of cones and sort of try and write things in terms of indecomposables. So it's natural to look at elements of S and see which elements are decomposable. But but we're interested in the set where Z is bigger than or equal to W. So we want our decompositions. But if gamma of Z is bigger than or equal to W, and Z is equal to the sum of Ci, and gamma is the sum of Ci gamma I, this is only interesting to us if each Z of gamma I is also bigger than or equal to W. Because otherwise we're getting a we're not telling anything about the cone. We're kind of leaving this set where Z is bigger than or equal to W. So we would know this was true so to fix this, I should say Zi is bigger than or equal to W, when Ci is not 0, right? I mean, otherwise if Ci is 0, that's boring. So to make sure this happens, we say a decomposition is increasing. A decomposition like star, decomposition star is increasing if for each Ci not equal to 0, we have Z of gamma I is bigger than or equal to Z of my original gamma. So all the terms end up having bigger z's when I decompose them. Now this seems like a weird thing to look at because you sort of think of things getting smaller when you decompose them. But in fact, we'll see if one looks at this, you see that this is not the case because this is a weird, this weight z is a weird kind of weight. And it's just mapping it to the file group. So there's no reason, it's not additive at all. There's no reason to believe that when you decompose, a priori, you don't know whether things would get bigger or smaller. And so we're interested in the case where actually things get bigger when you decompose them. And so then we can look at we can define the set of irreducible elements of S to be the elements which do not have any increasing decompositions. That little arrow up is to indicate increasing. So this is a set of elements of S which do not have increasing decompositions. And so then the first fact is that, so then one can show is the following proposition, is that any element of S can be written as a non-negative linear combination of elements of. Now this seems like it should be totally trivial, but it's not quite as trivial as you might think because first of all, the sets S might be a little complicated. There are just some inversion sets of file groups, and you're allowing yourself to decompose things with rational coefficients. So here's an example to show why it's not completely trivial. I mean, in the end, it'll sort of work out. So consider in B2, let's just say S is equal to, so we can take the long element of the file group. So say we take S to be the set of positive roots, which is just epsilon 1, epsilon 2, epsilon 1, minus epsilon 2, epsilon 1 plus. Okay, so say you want to try and write an element as in terms of indecomposables. Well, your natural thing is just to start decomposing. But suppose we were stupid and we made a choice like, suppose we wrote epsilon 1 as 1/2 epsilon 1 plus epsilon 2 plus 1/2 epsilon 1 minus epsilon 2. I mean, that's allowed because we're using rational coefficients. You see, now what you could end up doing again is you could kind of try and, okay, I'll keep decomposing. I could say this is 1/2 epsilon 1 plus epsilon 2 plus 1/2 epsilon 1 minus epsilon 2 plus epsilon 2 plus 1/2 epsilon 1 minus epsilon 2. So you've made kind of a bad choice, and if you keep going on this way, you can iterate this process forever so it doesn't terminate. So of course we can get around this in this particular example. So here, the actual set that we want, it's actually the set of simple roots. It's epsilon 1 minus epsilon 2, epsilon 2. And then in fact, we see we can actually do this, of course. If we did a decomposition the smart way, we would have actually gotten everything as a Z combination. But this is a complication when you're using Q decompositions, which you don't see. If you were only allowing integer coefficients in your decompositions, you would never have a problem. The decomposition would always have to terminate. But because you're allowing rational coefficients, a priori you could end up with some process that didn't terminate. So this proposition, although I mean, my advisor once said that some theorem had to be easy because it didn't use anything. And this is actually very general. I mean, it doesn't really use anything. So he would say it's easy. So, but it's a little bit non-trivial. But then, so then what happens in this case? So once we know this proposition here, if we look at the cone, so now back to the set S of Z intersect ZW. So we want to show that S of Z and bigger than or equal to W is contained in the cone of S of X bigger than or equal to W. So by the proposition, it's enough to show that the set of irreducible elements that don't have an increasing decomposition the set of irreducible elements satisfying z less than equal to, bigger than equal to w. But then then it turns out through some sort of miracle is that sort of the following proposition, which is that if gamma is an irreducible element of S, then the weight z of gamma is actually equal to the weight x of gamma. So maybe I'll say gamma I. In other words, that means that S1, Si hat, Sn, or this, I should say this follows from the statement that this state, in fact, which is true in this case, is reduced. So if you're an irreducible element, then your z hat is your x hat, and so therefore if you're in the z set, then you're automatically in the x set because your z and your x values are the same. So if gamma I is in irreducible S of z bigger than or equal to w, then z of gamma I is bigger than or equal to w. So that means that x of gamma I is bigger than or equal to w. So that implies that, so gamma I itself is actually in S of x bigger than or equal to w. So in fact, the irreducible elements, these two things, the z's and the x's, are the same. Now, why is this actually, so why is it true that if you're an irreducible element, then your z set is your z is equal to your x? So why is this proposition true? So I guess, so what I want to say is, so I mean, this is connected to some related notion of decomposition. So it's connected to, so I mean, maybe let me back up for a second. So if S1 of the Si of the Sn is not reduced, then what happens? So it turns out that one can find indices j and k such that I is between j and k, and such that some multiple of gamma I is equal to gamma j plus gamma k. So this is the kind of thing it's close to the kind of thing you find in Humphreys where he's talking about just these kinds of exchange conditions and all this kind of stuff. But if you have this condition, you can find indices j and k such that this is true. I mean, basically the kind of idea would be something like, you would look at, if this index was not reduced, what you could do is you could say something like, well, the idea would be something like, k is the smallest index such that you have something like the length of S1 of the Si hat up to Sk is less than the length of S1 Si hat S of k minus 1. So because it's a non-reduced expression, at some point the length has to go down when you decrease these things. And so So you take, if you let K to be like the smallest index where this is true, and you take J to be something like the largest index where something like, if we take, say, I guess, well, I forget exactly, it's something like the length of Sj to Si hat up to Sk maybe, K minus 1 maybe is less than S of, or maybe it's S of K, is less than the length of S of J plus 1 Si hat Sk. And if you do, and basically, you know, because these expressions are non-reduced, at some point the length doesn't keep increasing when you're multiplying elements. And if you pick those indices out in this way, then you can play around with some file group calculations, and you get that you know, you get this relation between these sets here. So that's sort of, so that's how one can do that. And so therefore the point is that if, so the point is that if z of k is not equal to, gamma is not equal to x of gamma, then this implies that S1 up to Si hat is not reduced, because I said, as before, I said that z of gamma I is not reduced, because if they're reduced, it's equal. And then that implies that gamma I equals gamma j plus, well, c times gamma I is gamma k plus gamma j. And moreover, by playing around with the file group, one can see that zj is bigger than or equal to zi, and zk is bigger than or equal to zi. So that's an increasing decomposition. So in other words, if, so what we've sort of done the contrapositive, we said that if, so basically, I guess what we wanted to say is if gamma I is an irreducible of S, then zi equals xi. And what we did is we did this by the contrapositive. The contrapositive is that if zi is not equal to xi, then S1 up to Si hat to Sn is not reduced. And then this says that gamma I equals gamma j plus gamma k, and that's an increasing decomposition, so gamma I is not irreducible. Okay, so I think that's all I wanted to say today, but so I think I'll stop. I think it's kind of interesting how this, you know, this notion of decomposability is connected with the Bruja order and the zero Heca algebra in this kind of surprising way, in fact. And so that's, and how you can get this kind of relation which looks rather like the Carrell-Peterson condition, except of course it's not as good. So I think there's still, you know, I still don't completely understand. This is not a complete description of the tangent spaces by any means, but it's interesting that these cones are the same, even though they're the spaces, the sets are different. So that's all. I think I will stop.
Can you go back to I guess it's the part on type A printer.
Yes.
Okay, so I guess with the type A result, people can do like the dimension.
That's right.
So in the other types, can you compute the dimension?
I don't think so, unless you compute the tangent space.
So that's still.
I think so. I mean, for classical types, there is this result of Loxton which does give a description of the tangent space in every type, but it's really quite complicated. I mean, it involves like, even the Bruja order in type D, if you describe it with subsequences of sign permutations, is quite difficult. Is a little bit complicated with parity issues and stuff. And so, if you look at the conditions for this to work out in type D, it's a rather complicated description. So in any particular example, you could calculate the set, but I don't know that you could come up with any nice way of saying what the dimension of the tangent space is.
So kind of in practice, for any one example, you could possibly.
Yes.
But in exceptional
To my knowledge, there's no explicit description. I mean, somebody probably has worked out G2 somewhere. I mean, but I don't know of any explicit description for the exceptional types. For certain elements, certain Schubert varieties, it's known. So I mean, for certain points X, it's known. So for example, if X is like a co-minuscule point of the Weyl group, which is like in type A, that would be like a Grassmannian permutation. So in the exceptional types, there's also these sort of corresponding elements of the Weyl group, and for those cases, you can describe the tangent spaces explicitly. But so it's basically like for the co-minuscule, those correspond to the co-minuscule G mod P's, which are like the simple. So you can do it for those, but otherwise, I don't think it's generally known.
Are there any nice conditions on the
Well, you can tell if it's I mean, there's various ways you can tell if it's a smooth point that are type independent, but like that involve like so this what sort of underlies this fact one, which I probably shouldn't have shut off my iPad, but I was thinking it was done, but these that fact one, which I didn't discuss, that the weights of the tangent space are contained inside this cone of weights, that actually uses equivariant K theory. And Kumar, for example, has a result. If you can do a calculation in equivariant K theory of the pullback of this Schubert class to the point, and and Kumar proves that the point is smooth if only if the pullback looks like something. So again, of course it's a type independent, and it's a very nice type independent thing. It involves you to do it requires you to do a calculation for any particular type, so it would be hard to. But then there was some work of Billy and others, Lakshman and stuff, where they were calculating they've sort of come up with maybe some combinatorial ways of figuring out the smooth points of the Schubert varieties, and so you don't have to do that complicated calculation every type. So there's some more combinatorial description, at least for the classical groups. And I think for the exceptional groups, it's probably all been worked out because it's a finite computation, and I think somebody could program a computer. Even in E8, it's probably, I don't know, in E8 it might be challenging to do this computation, but somebody could probably do it.
In the base theorem, do you suppose you need the full rational code, or do you suppose you can get away with converting the field?
I don't know. In simply laced types, you can get rid of you can use dude over Z, and so for the other types, for non-simply laced, I'm not sure how much one has to.
recording here?